Hello, we are Rupti. Today we will talk about the title of deep learning, data mining and the machine learning tool about deep learning approach for image-based American Sign Language recognition. For introduction, we would like to talk about our motivation and objective, as well as research questions for the project. As we know, effective communication relies on language proficiency. There are some people still struggling with spoken language, as the World Health Organization predicts a significant rise in hearing loss case necessary inclusive solution. And ASL play a crucial role in the linguistic identity of the deaf recognition to the deaf and hard of hearing community. So that we would use advanced in deep learning, particularly in image ASL recognition, to offer potential solution to communication barrier. So that our research question is that how can CNN effectively recognize and interact ASL register in image? The objective of project is to develop a model using CNN to empower individual with hearing loss. The research aims to advance sign language recognition technology through deep learning, enhancing accuracy and efficiency. The goal is to create a more inclusive society where communication barriers are reduced. For some related work that we will research before, sign language recognition has transformative potential for enhanced quality of life in the deaf and hard of hearing community. For some study included ASL, Filipino, Indian, Italian, and Turkish, and deep learning have particularly convolution CNN have gained some significant professional in image and video recognition. Among those applications were applied CNN, LSTM, attention-based network, transformer network, CAPNet. It states that this advancement have a potential for more effective communication and improve the quality of life for the deaf and hard of hearing community. Next to
Yeah. From here, I will take. Thank you, Thui. After the related work, as explained by Thui, moving to the methodology part, we are using a dataset which are having three different folders. In one folder, we are showing that the dataset is raw. There is images of hand sign languages using different where there is a different illumination lights, and we have put the images taken from farther and nearer to the hand. And then there is some folder where we have added blank images. After that, there is a second dataset that we are using here that will be used as a pre-processed image. So the other dataset is data 80 and data C folder. So in data C folder, we have images that is transformed using K-NIH, and in data 80 folders, we have images that are processed using adaptive threshold techniques. So using those techniques, we are creating a model which will be divided into three different categories. Like one will be the evaluation, one will be the testing, and one will be our training data sets. So training data set will contain 70% of the data, and we have created three different models here. What we are doing is first we will create a model only for having training the unprocessed data. Then there is another model that will be training the AT data and C data. Then three models are evaluated, and there is one model that we have created using all the data sets. And then we are comparing the results, and we are using a model. And I will like to show you the model architecture here. So according to this model architecture, as you can see, we are using the first CNN model with 32 filters with dimension 3x3. This layer known as feature extraction capabilities and feature extraction capabilities, and this analyze the images through a convolution operation. And the dimensions that will be reduced to, it will be 256 256 cross 256. After this layer is completed, we are using max pooling 2D layer that will employ a 2 cross 2 pooling, and it will be reducing the images to 127 plus 127 with the 32 filters as already applied for CNN first layer. So by this, we will be reducing the size of the image for better efficiency. After that, we are again using a layer 2 of 16 filters, size 3x3, and the same goes with the same pooling for 2x2, that is by default pooling size. Then we will get a 62x62 image. And for the third layer, we are using again 32 dimensions filters, and with same pooling data as 2x2, and at last we will be getting the images of 30x30. Then we are flattening all these layers, and we are combining it with the dense layer with 256 neurons. That will be, again, we will be having a 256 cross 256 image. And then after that, we are classifying into 27 different classes in the last dense layer. And after that, the total count of trainable parameters you can see is 7,39,000. And by this, we are doing our model architecture for this, and the results will be explained by Tulio.
Nice. So with this architecture, we built 4 different models, which of them we fed with different type of data, one with raw data, another with C-treated data, AT-treated data, and one more model more generalist with all these types of data. Here we can show the model history. The loss and accuracy was really similar for all of them. And the first epoch, we had nearly for 98% accuracy for all these 4 models. We used this just 5 epochs here. So the results we have used for evaluation metrics, the precision, recall, and accuracy. We can note that in the diagonal of these tables, we have really high accuracies and recall and precision, because when you train the model with this specific type of data and you test it against the same type of data, the accuracy will be much, much higher. Another idea here was to check just if we train the data with one specific treatment, it could work when we try to predict in another type of data, and this is shown here that it's not possible. Like, for example, in the first table, we have model C trying to predict data without any treatment was almost 0% of precision. We can also check that in the confusion matrix. So the first 6 confusion matrix on the left are about the models with the less accuracy we got, like if we use C against raw data. And then we can see that in this matrix, they don't have a really clearly diagonal. Even for the last one, we have just 2 vertical lines, which means that the model couldn't detect any type of edge we had on the images. In the other side, we have 3 matrices that are about when you use the raw model against raw data, the C model against C data, and AT model against AT data. Clearly, we can see this diagonal since we had accuracy above 99% for these training sets. So we cannot generalize the use of these models, but with the model that we fed with all the types of data, we got really good results. For when we used it against data with no treatment, which is the first matrix on this image, we had more than 80% of accuracy, while from all the other sets that we had some type of pre-treatment on images, we got more than 98% of accuracy. What that means that we can build a general model that with almost any type of image treatment, it will work. We have these conclusions like the processing technique used to define how well the model would predict the classes of test data, and applying adaptive thresholding technique on test sets is recommended since we got the best accuracy with that. More diverse data builds best model. So more generalist model is better here. And so for future work, we suggest like other pre-processing techniques to test that also, and use even a more diverse data as input, and maybe also polluted image data sets. So maybe we could train even unseen data. Thank you from Group T.
Thank you.